my gas molecules. Okay? And I want to know what the pressure inside here is. What's the definition of pressure? Force over area. So I'm looking at force over area. What's my force?
30 kilograms.
30 times 9.8. It's going to be the weight of the piston. Weight is mg. Okay? You're getting that next 6 weeks. All right? But weight is mg. Over the area. What's my area? Almost. I'm going to use the radius.
50 thousandths pi squared.
Pi r squared. But I do need this in meters. So this is a 5 centimeter radius, right? It says 0.050 meters. That's 5 centimeters. Yes? Not 5 meters. Are we good? A 5 meter piston radius is like huge. Like, I'm not going to have one of those. All right? But you realize, I mean, a 5 centimeter radius is like that. That's a piston that's only like this big. Okay, big piston for a car. Right? Small piston for a big, big, big marine engine. Okay, so reasonable within its size. This area is pi r squared. So it's going to be pi times 0.05 squared, which would be 0.0025 times pi, so that's like 0.0075 or 0.008. This is like 300. So I'm going to take 300 and multiply by 5 and divide by 4. 1,500 divided by 4, so 375. So the gauge pressure, 30 kilograms. Who cares about the volume? Come on. Oh, off by 0. Right? So I said 375 would be 37. That's close. Right? So 3,700 pascals. That is not including the atmosphere. That's the pressure due just to this piston. Isn't the air pushing down on here? So I would have to actually include then 1 atmosphere to get the absolute pressure. And so we add those together, and we get a total. Think about where the pressure comes from and what type of pressure they're asking for. It helps to delineate between gauge and absolute. Do remember, if this goes and you, I didn't get the whole problem down, where are you going to find this PowerPoint?
On our flash drive.
On your flash drives, right? So you have absolute access to it. All right, so now we are down to 120 meters. Calculate the total pressure on the exterior surface. Total pressure. That's going to be an absolute pressure. Where's the absolute pressure going to come from? Well, doesn't it have the pressure of all the water? And isn't the air pushing down on top of the water? So I add both of those. I'm going to add 1 atmosphere of pressure plus what's the pressure due to a column of fluid? Look at your notes. You ought to have that one written down.
1,000.
So I'm going to do P1, which is my atmospheric pressure, plus rho GH. The column with the pressure due to the column is going to be rho. But now this is 1.03 grams per cc. How do I convert that into kilograms per meter cubed?
Dimensional analysis.
Dimension analysis, or what's the shortcut? Well, let's consider this. 1 gram per cc, the density of water, has a equivalent unit of 1,000 kilograms per meter cubed. So what's the multiplication factor between grams per cc and kilograms per meter cubed? 1,000. So the density of seawater is 1,030 kilograms per meter cubed. What planet are you on?
Earth.
Because we're the only planet that we know that has submarines. Just saying. Right? And a depth, my height, 120 meters. So I'm going to do rho times g times h plus 1013 times 10 to the 5th Ready? And there you go. Does the problem solving strategy here make sense in dealing with pressure? Pascal's principle. What does this get me to do? What's Pascal's principle? Okay, we're going to use the fact that we're dealing with an ideal fluid. And what's the important criteria of an ideal fluid?
Non-viscous.
Non-viscous, but we're not using that one. The first one I said, it's incompressible. Okay, what that means is I can't squish it together. Okay, it doesn't have springiness to it. All right, when I can compress something, I get to store energy because I've compressed it. If my fluid is incompressible, I can't do anything. I can't store energy. I can just transfer stuff. All right, think about this. When you are driving in your car and how do you stop? What do you do? Put your foot on the brake. Are you actually then stopping the car? No. What's the process that happens? Well, obviously, no, I think you don't know. Saying I don't know is going to be a good one. First process is you're pushing on a pedal, which is a simple machine called a lever. All right? And that lever action then goes against a master brake cylinder. And you are compressing fluid in a master brake cylinder. All right? You compress that fluid, and what it does is it sends fluid through all these other lines to the 4 wheels, and they have brake shoes that now get pressed against something that's spinning. If brake fluid was a compressible fluid, you'd put your foot on the brakes and your brake pads wouldn't move. You wouldn't want that. I want that incompressible fluid so that when I push on that fluid, the fluid has nowhere to go but makes the cylinders open up that press then on your brake pads and slow you down. All right? There's a direct connection between how hard you press and how hard your brakes press, because it's mechanical and it's a fluid. It deals with Pascal's principle. Pascal's principle says that if I put a change in pressure in one part of a system, I have that same change in pressure everywhere else. All right? And what does it get to us? So we're doing this. States that pressure applied to one place is transmitted to everywhere else. When I put a change in one, everything feels the change. So when you put your foot on the brakes and press on the master brake cylinder, the cylinders that have your actual brake pads feel that same change. Okay, that concept of Pascal's principles is why we have hydraulics. Now, what's something that is used for hydraulics? When they say hydraulics, what do they mean by that? Besides brakes, but that's a different thing. Yeah. No, they use fluid dynamics for the suspension. If you have a certain type of shock absorber, it has fluid that transfers, and that slows down your shock. Right? How many of you have ever been to a garage, and they've changed tires? Don't they drive your car up on a thing, put stuff underneath it, and then the car goes? Why does it do that? Okay, is a 3-year-old capable of lifting a car? Sure they are. Are you kidding me? A 3-year-old can lift any car. You get one of the nice hydraulic jacks, you put the hydraulic jack underneath there, and the 3-year-old's out here going at the end of that arm, that lever arm, right? And the car's going. A 3-year-old can lift a car. Because I'm going to use Pascal's principle, right? First of all, there's a long lever arm that he does that work for. So I got his force multiplied by that lever arm. And that lever arm's pushing on this little itty bitty piston. Right? So I'm taking force per area, but my area is really small. So when I have force per area, my area is really small, I don't need a big force to get a large pressure, right? But if I distribute that force per area over a big cylinder, now I have a big area. Won't it require or lift a big force? That's why I have a little 3-year-old pumping up a car. All right? So what's going to be the same? What happens here? Pressure in or pressure out equals pressure in. That's the Pascal's principle. That's that the pressure is the same. That on both ends of whatever I'm looking at, pressure has to be the same. So we look at this. Force per area, that's pressure, right? So everywhere in here, the pressure is the same. So this force per this little area is going to equal a much bigger force over a much bigger area. You follow that part? So I'm going to get F1 over A1, right? Because pressure is going to be force over area. So F1 over A1 is going to equal F2 over A2. Because my pressures are the same. That's your basic Pascal's principle. That's the equation that you want. That's what you're going to be able to use. Now, think about this. Doesn't this distance have to be a whole lot more than this distance? I hope that makes sense for everybody. Because the 3-year-old, doesn't he have to go for 7 hours, pumping up and down just to get the car to go 2 feet? He's moved through a whole lot more distance than the car has. Right? And you never get anything free because there's always friction involved, there's always things involved. But in an ideal system, work in would equal work out, I'd have 100% efficiency. But we don't. But in that case, in pressure terms, we do. So F1 equal over A1 equals F2 over A2. All right, problem. So here we go. In a hydraulic system, 200 cylinder has a thrust of 110, the weight required. So big over big area, little force over little area. Right? By what did my area go down? By what factor did my area go down? 100 to 10 is a factor of 10. So what is my force going to go down by a factor of? 10. So I only need a 20 kilogram cylinder to hold up a 200 kilogram cylinder. Oh, I did a whole lot of work there. 196 newtons, 20 kilograms. Can you follow that my relational factor was that of 10? A whole lot faster to solve. And at this point, when you take the quiz, wouldn't it be nice that you could take quizzes a lot faster? Yeah, but you'll get there. All of you will. All right. How am I going to solve this? Well, isn't the volume of stuff moved in the little cylinder going to equal the volume of stuff moved in the big cylinder? And isn't volume going to be area times height? So if my area goes down by a factor of 10, wouldn't my height have to go up by a factor of 10? If we're doing that same problem. Right? So if the large cylinder is pushed down 5 centimeters, right? That was the 200 kilograms and the 100